All right, well, today we're going to get into this concept of energy expenditure, and then at the end, the end of the week, we'll talk about fatigue more, but today will be more energy expenditure, how we measure that, what that is, how to do some calculations with that. So does everybody have their math brains on today? No? How can we get your math brains on? We need like a math warm up or something? No? It's not really intense math. It's not calculus. It's really just like basic algebra. So nothing too tricky. But I know math is a fear is a thing. Right? Yeah, fear of math, but it's really not complicated math. But let's start out with a couple of questions first. So I'd like you to talk through this one as well as this one with the people on your team. Okay, so we got kind of two questions here. So yeah, go ahead, talk through this one as well as the one on the next slide with the people on your team.
Yeah.
Yes, let's do it. Let's put something on the calendar after class. Okay. You nervous? Yeah.
Yeah, I'm really nervous.
Yeah. It's understandable. Yeah.
You're able to see all of mine, correct?
Yeah.
Okay.
I just copy and paste them all into a Google Doc, so I'll just grade it from there.
Okay, just I was gonna email you, but I figured.
Now we're all good. We're all good. Yeah, I actually told the IT people that I figured that out. I figured they would already know. They're like, no, we didn't know you could do that. Thanks.
Yeah.
Well, that'll be helpful.
Yeah,
So,
for sure.
yeah.
It helped so much. I didn't have to redo.
Oh gosh, that would have been terrible. Yeah.
It's happened before. My screen was black and white.
Really?
We did like we're on Zoom.
Yeah.
Still suck too. Turn off sometimes.
Totally.
What's the deal with that?
Yeah. Eesh. All right, guys, let's talk about this first one here. So what'd you guys think? It's kind of hard to hold up your fingers on this one with multiple answers, but is there one on there, if you had to choose one that you feel like would be the better? Okay, some people are saying A. Any others? Are there any others that kind of stand out as a broader definition? All right. Yeah, what do you think, Cole?
Yeah, I was going to say the reason why I chose U is because I think A through D all have the potential or the capacity to do work.
Yeah, totally. Yeah, for sure. So the capacity to do work in some sense is energy, right? And that work could kind of be expressed in a lot of different ways, right? But the other ones are all kind of forms of energy, right? Heat is a form of energy. Light it has energy in it. Whenever we move something, that is like doing work right there, that's mechanical energy, right? Pressure also has the ability to move things and create mechanical energy as well. So yeah, it really is kind of definitely, I would say all of these things are some version of energy. Capacity to do work is probably a little bit broader of a definition of energy, whereas the other ones are different forms of that, right? And then this one's kind of more fun, I think. But what'd you guys think on this one? First of all, let's start the same way we did before. If you had to choose one, which one would you choose? Hold that one up as a team. Did you guys have a chance to talk about this one? Yeah, okay. We got a few saying C back there. Yeah, so some saying C are the ones that are voting. The sun, right? And this is just kind of a cool concept, I think, kind of a cool thing that kind of transcends science and just kind of this idea that like everything comes from the sun. I mean, it is science, but it's kind of analogous to spirituality too, right? That all good things come from God. All energy, all life comes from Christ in a way, right? And so kind of in the same idea, all energy that moves and animates everything on this earth comes from the sun. It really does, right? Because plants can absorb that energy, right? We or other animals can eat those plants, right? We either eat the plants or eat the animals, right? And get that energy, right? And then we break that stuff down, make our own energy, release things into the air. The plants can then absorb our CO2, right? It's kind of this constant cycle, right? The cycle of energy and of carbon cycling. And so it's just kind of cool in the way. The reason I added E on there, right, is because we do. So one time the student asked me that, well, what about energy in the core of the earth? Because there are these types of power plants that like they drill down into the earth like miles and like can get like thermal energy from the core of the earth. But I guess if you think about the formation of the universe and of our solar system, the earth probably exploded from a star at one point, and so from the sun, right? And so that what's inside of the earth is probably came from the sun at one point too, right? So yeah, whatever, that's beyond my knowledge of understanding, but yeah, all those things are in one way getting energy from the sun, which is pretty cool. So when it comes to energy for this class, we need to think of a way or humans need to think of a way to quantify energy, right? How do we put a number to that, right? And so when it comes to biological energy, we're typically talking about calories, right? And so a calorie with a small c is the amount of energy in the form of heat that is needed to raise 1 gram of water by 1 degree Celsius, right? And so energy is a relative concept, right? And that's kind of where it's like the same idea as like capacity to do work is like the capacity to push something or move something or warm something up, right? So it's a relative concept. It only makes sense when it's relative to something else. And so this is just a perfect example of that, right? We can only measure it in terms of its ability to change the state of water, right? And that's one way to quantify it, okay? And so that's a small c calorie. But typically when we're talking about calories, like on a food label, we're talking about a big C calorie, which is 1,000 of those little calories, okay? Which is the same thing as a kilocalorie, right? So capital C calorie, kilocalorie are the same things. Okay, so when we look at a food label like this, we see that 1 gram of carbohydrates is how many calories? 1 gram of carbs is how many calories? 4, thank you, yeah. And then protein, how many? 1 gram, 4. Fat, good, you guys caught up with it. Okay, yeah, so those we're talking about kilocalories, right? Those aren't just small c calories, those are kilocalories, okay? So that's kind of how we quantify it in terms of food, but that's also how we quantify in terms of energy expenditure too, which is what we'll do here in a second, and what we'll do in the lab on Wednesday is we'll calculate exactly how many calories Ilse burns when she sits there at rest, when she walks at 3 miles per hour on the treadmill, when she walks at 4 miles per hour, and when she walks at 6. So that is something you could potentially take with you, Ilse, if you're interested in that, is that you'll get a calorie per minute number that you burn at 6 miles per hour. So if that's a running pace that you do often, 10-minute mile pace, then you'll know pretty much how many calories you burn every minute of running. So we'll look at that. Questions on any of that so far? Okay. All right, so when we look at the energy expenditure, right? So how many calories is somebody burning throughout a full day? We have a few different components to that picture, right? And these are all in the pie chart here, okay? So the biggest one by far is our resting energy expenditure. That's about 2/3 to 3/4 of the total calories per day. And obviously that depends on how much we exercise. If we exercise a lot, then resting energy expenditure would make a smaller amount of this pie chart, okay? But then we got some other things, right? This one we don't talk about much. It's called the thermic effect of food. This is like when you eat a meal, sometimes you notice that you heat up a little bit, right? Like this, the whole like meat sweat thing, right? That's kind of the same idea. You've eaten a large meal. It takes a lot of calories to deal with that, right? And so when you burn those extra calories, you heat up a little bit. That's the thermic effect of food, okay? But then we have the exercise pieces, right? So there's exercise thermogenesis, which is like our planned activity, right? We go out for a run, we go for a walk. That's something we plan to do. So that takes a little chunk of the pie. But then this one is kind of a more nebulous one. This one's known as NEAT, or non-exercise activity thermogenesis. This is all the little movements that we do that aren't planned activity, right? So this would be like, as I look around under the table, I see some of you doing this, right, with your foot, some of you doing this, some of you just are perfectly still, right? That makes a difference in the long run, actually, in your total calorie burning throughout the day. It's not just that, but it's, do you tend to stand more? Do you tend to sit more? Right? Those things make a difference too. So it's kind of this non-planned exercise that we do. And there's evidence to show that in certain situations, when you put somebody on an exercise plan that hasn't been exercising for a long time, in some cases, they will decrease their NEAT, that amount of extra movement they do throughout the rest of the day, to make up for that exercise that you force them to do, right? Or they force themselves to do, right? And in some of the studies, it's just wild. It's almost a perfect match. There's a couple classic studies like that where they, especially with elderly people, not elderly, but people like in their 60s, 70s, in that range. They took a group of people and they measured their energy expenditure like with some very precise methods before the exercise intervention. And then they put them on the exercise intervention that accounted for about 700 calories per week. And then they measured all these components of this pie chart, and they saw that their NEAT went down exactly 700 calories per week. So like your body just kind of sabotaging you, right? It's like a biological control of your energy expenditure that you're not even aware of, right? Part of that maybe you are aware of because you're like, man, I'm tired. I went for my run. I'm going to sit the rest of the day, right? Maybe there is some conscious part of it, but there's definitely some subconscious part of it too. And there's some other evidence to show that people's success in weight loss programs, it can be somewhat, not completely, but sometimes is related to the change in NEAT that occurs. Some people kind of react to intent, to increase in their activity by decreasing their NEAT. Other people don't, right? And so there's something there probably. But any questions about that? Okay, so that's kind of the pie chart thing. This thing over here, the questions over here on the left, when we break down ATP, when we make ATP and then break it down, we can only harness somewhere about 40% of that energy that's actually within those carbon-based molecules, right? And the rest of it is lost as heat. Okay, so what I mean by harness is like the amount of energy that we find in glucose, in fat, only a certain percentage of it actually goes to doing something useful in our body, right? Actually goes to moving us, to doing some chemical reaction, doing something like that, right? And then the rest of it's just lost as heat. But that's actually pretty good. When we look at a gasoline engine in a car, does anybody know about how efficient those are? So this is a measure of efficiency, right? We're using 40% of it. Anybody have any ideas on that? It's about 15 to 20% if we're doing good, right? So the rest of that's all lost as heat. That's why your engine gets so hot, right? That heat is just lost energy, right? So because of that, because we know pretty much that a given amount of energy is lost as heat, we can actually measure that heat production and get a good idea of how many calories somebody burns, right? And so that was kind of that's what this direct calorimetry means, is we're directly measuring, so we're measuring heat production. Okay, and so it's a way to measure energy expenditure. And it's really best for like long periods of time, like a full day, like 24 hours plus, kind of like. And so the tough part about direct calorimetry is you have to trap somebody in a little chamber all day, right? So nobody really wants to do that, right? But it literally is measuring exactly how much heat their body's producing, right? If you put something in there like a treadmill, you have to subtract that out, because that obviously produces some heat too, right? There, you're measuring, you're measuring oxygen, or oxygen's going in, CO2 is going out. You actually have to obviously ventilate the room to make sure it's staying livable. But yeah, so it's actually known as a very good way to measure somebody's like full body energy expenditure for a long period of time. And so because it's direct, because we're directly measuring heat production, we're directly measuring that energy usage. Okay, not super common because it's expensive and you know it's hard to do. You can really only measure one person at a time. And so yeah, so that's direct calorimetry. The one that we do in the lab is called indirect calorimetry. Okay, and this one, the one we'll do tomorrow or on Wednesday, looks just like this. Okay. So Ilse will put that thing in her mouth and we'll plug her nose so no air escapes from her nose. And it's going to go. So when she takes a breath in, air is going to come in this one-way valve this way. Okay. It's going to go in, obviously, into her mouth, down her lungs. And when she breathes out, it's going to go this direction. There's one-way valves that make the air only go that direction. Right. So and by plugging her nose, we're collecting every bit of air that she's breathing out. Okay. And by knowing the percentage of oxygen and CO2 in the air that comes in, and then measuring the percentage of oxygen and CO2 in the air that comes out, we can calculate exactly how much oxygen she consumed, right? And then how much CO2 she added to that air, right? And so that's pretty much what it's measuring. It's measuring exhaled oxygen, exhaled CO2, but then the third variable is ventilation, right? And really ventilation is a measurement of the total volume of air that passes through that device. And that's really what we need to measure first is the ventilation, because then that gives us a total volume of air that was breathed out. And then we can say, all right, of that total volume of air, what percentage of it's oxygen, what percentage of it's CO2, and then we can get those numbers. Okay, so that one is called a closed system, the one right here, because we're collecting all of the air, right? But then we also have these open systems, and we have one of these in the lab as well. Sophie, that's hanging out back there in the back, is going to be using it for her for her thesis, and that one's totally portable. So we can take it out, go for a bike ride with it, do whatever. That keeps all the data on the device. But it's open, so it's just sampling the air that's passing by it, and getting from that sample of air, it can tell you how much is oxygen, how much is CO2. Okay, and she'll actually be doing a fun study with it that you guys are all invited to participate in, which is you're going to do a CrossFit workout one day, and you're going to do a HIIT on the track workout one day wearing this thing, and then we're going to see which one burns more calories, as well as some other things too, like which one makes you want to eat more afterwards or less, and some other things. So yeah, so that's the open version of this. Okay. All right. Questions on indirect calorimetry? What that means? So direct is directly measuring heat production. Indirect is measuring O2 and CO2 and volume of air. And then we can use those numbers to calculate calories, and I'll show you, and that's what we're going to spend some time doing here in a sec. But in order to do that, we need something called the RER, right? And we mentioned RER before. RER is calculated by the volume of CO2 expired divided by the volume of oxygen consumed. Okay, this is just another version of indirect calorimetry called a hood. This is kind of the best way to measure somebody's resting metabolic rate. Is you put this whole thing over them, have them breathe in there, and then they just relax. You can relax a lot more when you're in that thing than you can having that thing stuck in your mouth. So that's how you do RMR. Okay, so with respiratory exchange ratio, we're going to go back to these equations here. Okay, so what's this guy right here? Glucose. There we go. Glucose. C6H12O6. Okay, that's glucose. As we talked about before, to burn 1 mole of glucose, it takes 6 moles of oxygen, right? And then we get exactly 6 moles of CO2 out of that, right? Well, there's 6 carbons, right? So that's how we get the 6 CO2s there, okay? So what we do for RER is we just look at the ratio of CO2 divided by oxygen, right? So for this one, it's just 6/6, right? So that's 1.0. Okay, so the RER, I guess I'm just going to do it down here. RER for burning glucose is 1.0. Okay, and then a typical fat, the most common fat that we burn in our body is called palmitic acid. It's a 16 carbon fat. It's right here. So it's got 16 carbons, takes 23 moles of oxygen to burn it. Okay, but we get 16 moles of CO2 out of it. All right, so if we put our 16 over our 23, what does that give us? It tells you right there, right? 0.7, okay? So we'll be doing this in the lab. You'll see these numbers come up on the screen when Ilse is exercising. And if our RER is 0.7, that means she's burning 100% fat. If our RER is 1.0, that means she's burning 100% carbohydrate, okay? And what we'll see is if she comes fasted, which you don't have to come fasted, but if she hasn't eaten for a few hours, then the RER will probably be pretty low, somewhat close to 0.7 while she's resting. And then as exercise gets harder and harder, RER starts going up and up and up. Because, as we talked about before, glucose burns faster, carbohydrates burn faster, we get ATP quicker. And so as exercise gets more intense, we have to switch to carbohydrate burning to keep up with the demand, okay? All right, so why does that matter for calorie burning? It's because of this, because fats, when we burn 100% fat with our RER of around 0.7, the amount of calories that we get out of a liter of oxygen is 4.69. Okay, but then when we go all the way to the other extreme, when we're burning all carbohydrates, and our RER is 1.0, the amount of calories we get when we use a liter of oxygen is 5.05. Okay, so it's just the way it is based on those calculations we just did. Okay, so then really what all this comes down to is an equation that we can use when we're doing indirect calorimetry to calculate somebody's calories burnt. All right, so we got kcals equals their VO2 in liters per minute. Okay, so that's the first variable that we need. And then we got this thing, which is directly from this table here. Okay, so the RER kcal equivalent, we see what the RER was, we go to that table and we use that number that's next to it in the table. Okay, and then we just need to know how long were they exercising at that VO2 and RER for, times it by those minutes, and that's it. That gives us the calories burnt. Okay, so we'll do a couple practice equations with that in a second. Questions on that so far? Okay, let me just talk about this fat burning zone thing for a second. How many people have seen something like this graph on like an exercise device or something? Yeah, and how many people have attempted to exercise at the fat burning zone? Anybody tried? Yeah. What does it feel like, Sergio? Does it feel hard, easy, somewhere in the middle?
Kind of hard to like maintain that zone.
Okay.
My heart rate goes too high sometimes. And it's like,
Your heart rate goes too high. Yeah. What about you, Peyton?
I always thought that fat burning was, when your heart rate was a little bit lower.
Mm-hmm.
Because it's not working as hard.
Yeah. Yeah, totally. And it is, right? That because of that thing I just said, as soon as exercise gets more intense, we have to switch over to carbohydrate burning because our body just can't keep up with fat burning. Okay. And so you can see it right here. The yellow would be like the fat burning zone, which is only about 55% of your maximum heart rate, right? So most of your maximum heart rates is around 200, right? So we're talking about exercising at a heart rate of 100 or 105, right? Which is definitely no more than a brisk walk. Right. But kind of one of the exercise myths in here that really bugs me with this one is that because you're burning the highest percentage of fat that low, then that's the best place to exercise if you're trying to lose fat, right? But the problem is not the percentage of fat, but it's the total calories that you're burning, right? When you're exercising at this low intensity, the biggest thing that drives your calorie consumption is this, right? Is your VO2, right? Because you can see this number here only varies from 4.69 to 5.05, right? That's not much variance, right? But if we change our VO2 from 2 liters per minute to 10 liters per minute, that has a huge impact on that equation that we'll see in a second. So to exercise at maybe 2 liters per minute, which might be what it is at 55%, and then to go up much higher to an intense intensity, we're going to burn way more calories outside of that fat burning zone total. Our percentage of fat calories might be a little bit lower, our total fat calories will still be higher, right? Because the total calories was much higher, right? So it's just something to, one of those exercise myths that bugs me. But yeah.
I had heard of like this cardio method where essentially you do like a sprint for 20 seconds, then recover for 10, and then you do that for 8 minutes.
Mhm.
And does that kind of work with like just dipping in and out of that fat burning zone? So you're in there, but then you can't maintain it, so you drop down below it a little bit. Do you know how that would work?
That would be like a version of like Tabata is what you're describing,
Yeah.
which would be like HIIT, like, HIIT, but Tabata is even different than HIIT. It's like super short sprints is more considered almost like what they call SIT, which is like sprint interval training. But the purpose of a workout like that would not be related to the fat burning zone. It'd be related to the other side of things, which would be, let's push ourselves into the really high intensities, but we can only do that for a few seconds. So then we got to go back down and then go back up. So yeah, so it would be more related to what we can do on the top end versus the bottom end typically. Yeah, yeah, good question. Yeah. Other questions on that? Okay, well, let's do a couple practice equations here. Okay, so we can kind of walk through this one together, and then there'll be a few that you can work on with your team. Okay, so this gives us all the numbers that we need. So you guys can just go ahead and write the equation here that we need. So we got calories is going to equal VO2, and we'll include the units this time so we can see how they cancel. VO2 in liters per minute times this, we'll call it the RER to kcal thing. Okay, and that's forget which one's first. Yeah, it's calories first. So that the units for that one is going to be kcals over liters of oxygen, and then we're just going to times that by time, and then the units for that one is just minutes. Okay, so just on your own for a sec, plug in those variables. You've got them all here, right? And then yeah, go ahead and do that calculation on your own there for a sec with those 3 variables. And so you have to go back to that table and see what the RER of 0.8 gets you. So when you plug in those variables, it should look something like this, right? We got our 2 liters per minute, that's our VO2. We got our 4.80, which we got from the table, right? The 0.8 over to 4.80, okay? And then we just got 30 minutes, okay? And yeah, so then we just multiply those 3 together. So what do we get there? What's our answer? 288, okay, so we got 288. And then it's good to recognize how the variables cancel out to get us our end units, right? So we got a liters of O2 on top right here, and we got a liters of O2 on the bottom right there, right? So those 2 are going to cancel out, okay? We have a minutes on the bottom right there, and then a minutes on the top right there. So those are going to cancel out, all right? So what we're left with is calories. There we go. Okay, questions on that at all? Okay. All right, so another way we can use this is to calculate somebody's resting metabolic rate. Okay, and I will give you some of these numbers here, but then you're gonna have to, then you can do the equations here. Okay, so average VO2 at rest is probably somewhere around 0.2 to 0.3 liters per minute. Okay, so let's just call it 0.25 liters per minute. okay? Whereas the average RER at rest is going to be closer towards the fat side of things, closer to 0.7. But let's just call it 0.75, okay? And then how many minutes are there in a day? How many hours are there in a day? Huh? 24, okay, 24, we're gonna times that by what to get our minutes? Say it again now. 1440 is how many minutes there are in a day, okay? 1440 minutes, okay? So yeah, I'm gonna have you guys do this one along with the other one on this slide here in a second. This one, you have to do a little bit of converting, okay? Because there's two different ways to express VO2. And actually the more common way is this one right here. Okay, so this is in milliliters instead of liters, but then we divide it by their weight in kilograms. And that's just a better way to do it, because the number one thing that tells you what somebody's VO2 is going to be, or the best predictor of somebody's VO2 is their body size, right? Because they have to carry their own weight, right? So if I want to compare my VO2 max to Sophie's, if I do it in liters per minute, mine's going to be way higher than hers. But if we both divide by our body weight, then we'll probably be pretty similar. Well, she'll probably have a higher VO2 than mine. She's more fit than I am. But you see what I mean? So that weight is the biggest factor there. And so we need to divide by body weight. Okay. So in order to get us back to the way to be able to work with this, we got to get it back into liters per minute. Okay. So you've got his VO2, you've got his weight there, so you can do that, and then you got to convert from mils, okay? But then the other part is nobody exercises at their VO2 max for very long, right? That's his VO2 max. You exercise at a percentage of that, and so that I give you that there. Okay, so work on these two problems with the people on your team. So get this metabolic rate here, total 24-hour metabolic rate, and then work on this one as well, and we'll come back together and make sure we're all on the same page. Okay, go ahead.
Seventeen oh six.
70 milliliters. 70 milliliters.
What's your VO2 max? Have you done it? Have you done max test? You've never done one?
No, but I did the 4x4 hit, and then the peak was 48, I think.
Wow, okay, that's good. VO2 is higher than mine then, I bet. But you probably got close to max on that, but
Yeah.
yeah, you might be in the mid-50s then. That's
Maybe.
good. Yeah, you gotta do it.
I know, I just don't really want to.
Yeah, I know. Because of the pain, yeah.
I'm so in touch. I'll do it though, like, when we're
Yeah,
doing
some of your
our-
pilot testing.
Yeah.
That'd be good. Yeah, you guys should definitely be your own pilot subjects.
Yeah, we're gonna test it.
Yeah, good.
Maybe Bod Pod, VO2 max,
Cool. Do the workouts too.
do workouts, yeah.
Cool. I've talked to a couple different undergrads that might be interested in helping you guys out.
Okay.
We'll see. But yeah.
Okay, awesome.
Yeah, cool.
Sounds good.
Yeah. You write in with the mouse.
Yeah, isn't it terrible?
That's hard.
It's just like, I could write it down. I just
Yeah.
didn't feel like.
Yeah, it's just, that looks pretty good. You're doing it pretty good. It's just hard to do.
Yeah, it just keeps correcting you, which is.
Oh, really?
It's just like, just stay.
Oh, yeah, you can do it to Xbox. Yeah,
It's
it's too easy.
Yeah.
When you see
58,000.
a food item store and it says calories.
Yeah,
Is it in kcals?
kcals, yeah.
That's so misleading.
Yeah,
It's like 250 calories. That's like 250,000.
no,
Is that how that works?
no, it's the same. Yeah, you're,
American calories or British
Oh, now I'm more confused.
usually, I mean, in Europe, they usually use joules for everything too, like mega joules. So it's totally different,
That makes
yeah.
much more sense if you actually go
Yeah, but this, what'd you get for this?
58.32.
No,
No,
it's more than that. Yeah, it's not right. You're off on the conversion there.
okay.
So it's 3.43 instead of 4.9. Then you multiply that by 4.6 and then, yeah. So you have, so this is.
Check with Georgia back there.
Yeah, if you did.
How we doing? What'd you guys get?
We were just working out like there.
Almost there? Yeah, cool. Can you hit those buttons? Right, Elsa? Yeah, when I had an Apple Watch, I tried to do it and I would just hit everything else. That's like the bigger screen one though, maybe that's a little better. But
Well, no, but so you have like. So it's like
how'd it come out? What'd you guys get? End up with about 5,000, yeah. About 17, yeah, cool. Looks good.
What is this? Not make sense. Oh, go on. Listen for me.
How's it going? What'd you guys come up with?
I'm already failing at basic math
Yeah.
again,
Uh-oh.
so not very well.
And then you.
Dude, I thought when I got.
What'd you guys come up with? About 5,000? Yeah, that's good.
That's not the case. I have to take, did you know, Dr. Stewart, that grad schools don't accept AP classes?
Yes.
I literally thought, I literally
Yeah.
had no idea, like, no one ever told me this, 'cause I took AP stats and I passed the test.
Oh,
Never thought I had to deal with it
Yeah.
until I looked at the prereqs and was like, does
Yeah.
one accept AP? And I was like,
uh,
I have to take it again.
shit.
I was like, not to cry, I was like, I don't want it.
Who's your advisor?
Cosby.
Okay, she knows that.
Yeah, I don't think she
Yeah.
realized it.
She knows that, but she got to tell you.
I was just like, I need to talk with her. Like,
Yeah.
I'll do the grad,
You gotta check, that costs $120.
they already charged it to my tuition.
Doesn't they charge you for
Yeah,
it?
they charge you for it.
120.
I didn't know that.
Is that stupid?
That's great. I didn't know they charge you for
Yeah,
it.
I was like, our tuition
Is that just the graduation fee though?
No, even if you're
That's
not
just for the
walking.
check? It does, that's not like the application, because you gotta
No,
like
that's the
apply
app-
for
it's the
graduation.
application.
Oh, that, okay, it's not just the grad check.
I just think it's stupid because like we pay tuition. I feel like it should be.
I feel ya. I feel ya, yeah.
Yeah, I didn't put my.
How do we do?
Good. I got 3.43. I realized I didn't factor in his weight.
Gotcha.
So
Yeah, it seemed like more than just a units issue. Yeah, so that was it. Cool. You guys get it? Okay, 5,000-ish. Yeah. Cool. Okay. What did you guys end up with on the 5,000? Yeah, good.
I had a reshape.
About 5,000? Good. Cool. Good stuff.
Oh, go ahead. Oh, this, yep.
Oh, yeah.
I don't want milk.
That'd be true. Did you not like the card? So.
This one, I remember. I feel like I'm back.
All right, guys, let's go ahead and come back together. Looks like most of you are done. So let's do our resting metabolic rate one first. So yeah, so we got our kcals equals, oh, doesn't have two L's. Kcals equals, all right, so we got our 0.25 liters per minute times, so 0.75. If we go to the table, what is that? What do we get from that? 4.74, okay. 4.74. And that one's kcals per liter. And then we got our time of 1440. Okay, multiply those together. What do we end up with? I don't know it off the top of my head. Somebody's got to help me out. 17 what? 6. Okay, 1706. 1706 calories. Yeah. Oh, I thought you said, yeah, so that's a pretty typical resting metabolic rate for, yeah, probably for a male. It just all depends on body size again, but yeah, we'd expect resting metabolic rate. And now this doesn't include any movement at all, right? So this would be like just if you're just sitting there all day, not doing anything, not eating, right? Because eating increases your by that thermic effect of food. Just that one part of the pie, right? The 70 or 65, 70% of that total energy expenditure there. Okay. So we might see that range as low as 1200 for much smaller people, up to maybe 2200 for much larger people, somewhere in there. But that's not the total amount of calories you should be eating for the day, because you don't just sit there and don't eat anything, right? There's the other calories on top of that, with the other parts of the pie chart there. Okay, so, all right, any questions on that one? Okay, so then this one, multiple ways to convert this, or different ways to approach this, right? You could do all your conversions first and then just get to liters per minute of VO2 and start there. Or you could actually calculate it, you know, do the equation first and then convert. You can do it different ways, just depending on how you want to do it. So let's go ahead and do the conversion one first. So let's start with this first. So we got 70% of VO2 max. If this VO2 max is 70, which is high, right? This is a professional cyclist. And also this is actually realistic too. If we look at like Tour de France riders, this would be like a typical calorie burning per day, right? And if you've ever watched the Tour de France, they do this for like 3 to 4 weeks straight, right? And so like there's no way to do you know, that amount of activity without losing weight. You just can't eat that much, right? You can't eat an extra 5,000 calories per day for 3 or 4 weeks, right? It's just not possible, right? So, but they are trying to eat as much as they possibly can so they don't lose much weight, but it's just so many calories that they've lost, right? So 70% of 70, what's that? Anybody do it that way? Say it a little louder, Kat. Okay, so you converted first, yeah. So let's do that. So we'll convert first. So 70 mils equals how many liters? What do we got to do with that? Okay, so we move it over how many places? 3, right? So we take this and go 1, 2, 3, right? So 0.07 liters per minute. Okay, and now we need to take 70% of that. And what's that? Okay, 0.0175. That's not right. What did we do wrong? Yeah, what are we doing wrong here? So we have 70 mils per kilogram. We need to convert that to liters. So we went 0.07. Notice, did anybody else do it this way? Okay, what's another way somebody did it? I'll use somebody else's method, yeah.
Yeah, just multiply mils times his weight to get that.
Okay, yes, we got to do that first, yeah. Oh yeah, so this probably is right, Cole. We just didn't do the weight part, yeah, yeah. Yeah, so we got that. So mils times his weight. Will somebody do that one for me? Do the 0.0175 times his weight, which is 70 kilograms. What does that give us? Do that one for us, Cole.
Times 70 kilograms.
Yeah.
1.225.
1.225? Yeah, that's still too low. All right, we got messed up on that one somehow.
I think it was because I did the 70% and I subtracted it from 0.07 to get 0.01.
Okay, so we'll go with Alex's method of, so Alex, you just took the 70 and times it by 70. Yeah, okay. And so then what does that give us?
So that comes out to be 4,900, which we need to convert it to liters.
There we go, 4,900. Convert that to liters, we go 1, 2, 3. So we get our
70% of that.
4.9 times it by 0.7 to get 70% of that. And we get what? 3.43. Okay, so now we got 3.43. We're going to times that by the average RER was 0.85. So what number do we get there? 4.86. And then we got to get, how many minutes is 5 hours? 300. Okay. And that gives us the 5,000.9 or something, right? Something like that. Yeah. Cool. Okay. So yeah, there's just different orders of things in the way you can do that, but you got to get it to liters per minute. And then you got to take 70% of that and just plug everything back in. So during the lab on Wednesday, you'll be doing a bunch of practice calculations with the numbers that we see on the screen. And so we'll continue on practicing that. We'll see you guys on Friday, but you'll see Dr. Lynch on Wednesday in lab.